We conclude our look at the sigma point common filter for state estimation by implementing it on the full enhanced self-correcting cell model. And to do that, we refactor the code just like we did for extended common filter into three separate portions. The wrapper portion is kind of like the operating system that will feed data to the initialization procedure, and then every measurement interval it will feed the new data to the update procedure, and it will do all of the plotting. And so then we have an initialization code, and we have an SPKF update code also. The structure is exactly the same. There are a few details that are different, as we will see when we go through, but I'm going to go through this probably a fair amount more quickly than I did for the EKF, simply because there are so many similarities. So looking at the wrapper code, what we're doing, we are loading the cell model, we're loading the data to use to feed to the filter, setting a temperature. We are extracting time, current, voltage, and SOC the same way that we did before. We are reserving space for the state of charge estimate and the state of charge estimate bounds. And we are using exactly the same initialization of the state uncertainty and the covariance of the process noise and sensor noise as well. This line is the same in idea but different in details from what we did for EKF. We are creating a data structure to be used by the SPKF iteration, much the same way we did an EKF data structure last time. We have a different procedure for doing that called init SPKF, but it takes exactly the same input parameters, so a voltage, a temperature, a covariance, and a cell model. Now I enter the main loop of the estimator. I open a weight bar like I did before for a progress bar. I measure, if you will, sample the present voltage, current, and temperature, and I iterate the SPKF equations exactly as I iterated the EKF equations before. So the calling prototype for this is the same as for EKF. I pass in a voltage, a current, a temperature, a time step, delta time step, a sampling period, and the SPKF data structure, and it returns to me the state of charge estimate, the state of charge bounds, and the SPKF updated data structure as well. Exactly the same in concept as for EKF, although the details of how that works internally are going to be slightly different, as we will see. Then I update the weight bar and close the weight bar when we're done, and I plot some things just as before, so no surprises there. The initialization code is very similar to the EKF initialization code, but there are a few distinctions that we need to point out. Again, I am deciding where in my state vector I have the diffusion current, the hysteresis, and the state of charge. I am again computing the initial state of charge estimate from the initial voltage estimate and computing an initial state exactly the same way as I did for EKF. No change. Then I am storing, as I did before, the initial state uncertainty, the process noise, the sensor noise covariances, but I am pre-computing the square root, if you will, of the noises that don't change. So sigma W noise doesn't change, sigma V noise doesn't change, so there's no reason for me to have to do the Cholesky factor of those every time through the loop. I'm going to save those and augment them with the Cholesky factor of the uncertain state in step 1A when I need to. And Q bump is the same as before. There are some SPKF specific variables that I need to compute. So first, how long is the state? Let's save that. How many outputs are there? Let's save that. How many inputs are there? Let's save that. How many process noise and sensor noise inputs are there? We'll save those. And then what is the size of the augmented state? Well, it's the number of non-augmented state plus process noise plus sensor noise, and let's save that. So those counting, those length parameters are, I think, all different. At least many of them are different from what we needed to save for EKF. And then I'm choosing here to use weighting factors from the central difference common filter method. I'm computing those exactly as we did in the previous example. Instead of using the rep mat, I multiply by a ones matrix, which amounts to the same thing there, but the same idea holds. So I'm creating a mean weighting and a covariance weighting set of data, and this here is identical to the initialization of the EKF code of storing the prior value of current and sign of current and the cell model. So everything is set up in memory. I've got all my constants and defines, everything just in one place, and it's all stored in this SPKF data structure, which is passed to iter SPKF and updated by iter SPKF every time we get new data. Here is the SPKF iteration. We again unpackage certain variables to local variables for easier access. So I unpack the model. I get the model parameters for easy access, and I unpack the some of the constants of the prior current and the state covariance and the state estimate and how many states there are, and some of these other things down here, how many process noise inputs, how many sensor noise inputs, the number of augmented states, the square root of the noises that don't change, covariances, and so forth, all of those. So up to this point, same idea as before. I'm unpacking data from this data structure that we're passing in and out every time. And now we start the SPKF itself. I need to create the augmented sigma points. And to do that, I need to have the augmented mean, which I actually do down here. I put the prior estimate on top of some zeros. So that's my augmented mean, but I also need the augmented square root covariance matrix. And we've already computed the square root of the process noise and sensor noise covariance matrix. That's the S noise variable. But I need to, every time step, do the square root of the sigma x matrix because that changes every time. So here I do the Cholesky decomposition of that matrix. To make the code a little bit more robust, I'm using an optional return argument from MATLAB. So the second argument, if it's positive, there was a problem in doing this Cholesky function, that the sigma x matrix somehow went negative definite, or at least not positive definite. And so I have some recovery code there because you can't just crash inside of a battery management system. You have to do some reasonable thing to recover from an error. And so I say, well, let's take the diagonal of sigma x, which should be variances of every state, and I'll take the absolute value to make sure they're positive, or at least not negative. And when I do, I'm going to then replace the sigma with the square root of these diagonal elements. So the sigma xa, I am saying it's at least as big as noise. So I'm saying it could be that I have noise, I have at least noise impacting me, or whatever the uncertainty was before is going to be the minimum. Now this is a design choice. You can replace this with anything you like, but at least you should have something here if we get this Cholesky decomposition error because our sigma x did not remain positive definite. And this, in my experience, can happen in real life, so you do have to have some code there. Again, it's round-off errors and so forth in the arithmetic that make it happen, because in theory that shouldn't happen. Okay, so I have the square root of the sigma x part, and I'm sticking it in my matrix by making my square root sigma x here and my s noise here. I could use the block diag command, I guess, but I'm just packing with zeros. So sigma x, zeros, new line, zeros, s noise in my square root matrix. Now I am calculating the augmented sigma points XA, and this line of code I think is exactly the same as what you've seen in the previous example, so I won't harp on that. And then the next line, I'm creating the predicted sigma points by passing the augmented sigma points through the state equation. And here I actually have a function later on called state equation that does that. So, just not to put all the clutter in the main code. So I pass the first nx rows, which are the sigma points corresponding to the state. I pass the input current. I pass the sigma points corresponding to the process noise to that state equation, and it gives me as output the sigma points for predicting a state. I do the weighted sum the same way as before to give me x hat. Now I do the error covariance time update, same as before. I don't think there is a slight difference here. This is a slightly neater way of doing it. So I'm doing XS for all of the points at once. So I'm taking the XX and I'm subtracting the mean from every point. And then after I subtract the mean from every point, this is an alternate way to implement that summation. So sum alpha I c times x minus x hat, xi minus x hat transpose can be written as x minus x hat matrix times the alphas. So this is diag alpha c all put together, and then times x minus x hat transposed in that matrix. So that's what I'm doing. It's a little neater way of writing it. You would think it would be slower because I'm multiplying by this diagonal matrix with a lot of zeros in it. Turns out in MATLAB, my experience is it's pretty much as fast as the other way and a little bit nicer to read this way of doing it. 1C, I save the previous current in the present current in I and the present voltage in Y. That's my sampling here. And I'm calling the output equation with all of the predicted state sigma points, the current, the sensor noise sigma points, the temperature in the model to get all of my output voltage sigma points. And I'm doing the weighted sum of all of those. And similarly, I compute the Kalman gain matrix using a slightly simplified form to what we saw in the last program. So y minus y hat matrix is scaled and so forth to get the, notice I've got xs from before times the weights times ys transpose, ys times weights times xs transpose does exactly what we want, and I compute the Kalman gain from those two covariance matrices. I don't think there's very many surprises from now on. I compute this residual here, the innovation, and if I get a really surprising measurement, I set the update to 0. Otherwise, I retain the optimum update. I update the state. I limit the SOC state. I could limit the hysteresis state here. I didn't do that. Probably an omission on my part. But I could certainly do that as we did with the EKF. Then I compute the updated error covariance, and I take special steps to help maintain robustness, as we've done many times before. If I have a really a surprising measurement, then I will increase my covariance as well, just as we did in EKF. and the rest of this is simply storage and returning back to the main code. Embedded in this function, we have nested functions for the state equation and the output equation. And here, xold is a matrix where each column is a sigma point representing a prior state estimate. Current is the current that I'm experiencing right now, and x noise is the process noise, I believe. So I'm adding to current this x noise. So I have a whole bunch of different noisy currents now. Used to be a scalar, now it's a vector, one for each one of the sigma points of noise. I initialize my state to be the same size as, so the output predicted state matrix is the same size as the input matrix, but it contains zeros for the time being. I compute the states corresponding to diffusion as the RC time constant times the old states plus 1 minus RC times the input current. I compute the hysteresis factor for every one of the states using the different noisy current for each one, and then I update the hysteresis state with AH times xold plus 1 minus AH times the sign of the current. And I update the state of charge as the old state of charge minus current over 3600 times Q. And then here I do put some limits on state of charge and on hysteresis to make sure that they stay within reasonable bounds. So that's the state equation. That's not doing that just for one sigma point. It's actually doing it using efficient matrix vector operations in MATLAB for all of the sigma points at once in parallel using these matrix operations. Then the output equation, again, similar idea. I pass it a whole bunch of x hat minuses in a matrix form. I pass it current, sensor noise, temperature, and the model. I initialize the output to be open circuit voltage using the different states of charge in x hat, and I add to this the hysteresis state appropriately scaled and the instantaneous hysteresis appropriately scaled, and I subtract from it the the diffusion resistor currents appropriately scaled to become voltages, and then the IR, and then sensor noise, and then I return. And then finally, you might have noticed up above that I had square root in all caps, and MATLAB is case sensitive, so that's different from square root all lowercase, and so I define my own square root function, which is what I call safe. I don't want to end up with complex numbers if for some reason at that point in time I happen to be taking the square root of something negative. I would never expect something negative when I was doing the square root, and if it was negative, that might be a problem. So first I take the bigger of 0 and x, so the result of that is not negative, and I take the square root and return that. So very briefly, very quickly, that is some code to implement a sigma point Kalman filter using the battery model. And we ran that code here. And the same exact test profiles as before were used. And in this case, I'm plotting over here. The estimate is blue, the truth is green, the bounds are blue thin lines. And it looks good at that scale, so we go over at this scale and we look at the estimation errors instead of the estimates themselves. So blue here, that's SPKF. Green here is EKF. And these here are SPKF and EKF bounds. What's interesting in this example, it's a little surprising to me actually, is that the EKF and SPKF bounds are very similar, although the SPKF estimate is actually a fair amount better, as you can see. So the SPKF error stays inside the bounds all the time, and the estimation error is less than 1% RMS, whereas the EKF estimation error was over 1% RMS. So again, that's a side-by-side comparison of the two different methodologies, nonlinear methodologies that we've looked at to estimate state of charge. Of course, we're estimating the entire state. I'm returning only the state of charge estimate, but if we wanted to know it, we're estimating the hysteresis state, we're estimating the diffusion currents. All of that information is available when I use one of these Kalman filter methods. So that brings us to the end of our discussion of SPKF as a method by itself. You're going to have some homework that looks at SPKF versus EKF, and you'll be able to evaluate them and make your own conclusions. In the rest of this chapter, we're going to spend most of our time looking at some real-world issues, maybe all of our time, looking at real-world issues in implementing this on a battery management system. Some having to do with the sensors being used, some having to do with faults on the sensors, where we talk about the chi-square test in a bit more detail, some having to do with initialization. But one big issue is speed. There's a really big concern by battery pack manufacturers with the complexity of EKF or SPKF. And they say, wow, we don't want to put on a supercomputer on the car just to run these fancy algorithms. Well, it turns out you don't need to. Using some refinements we talk about in the remainder of the chapter, you can implement SPKF for 100 individual cells in a battery pack on a pretty simple processor. We used an ARM7 fixed point processor with a floating point library, and using the refinements we're able to use only about 20% of the CPU, estimating the state of charge, or the state actually, of all the cells of a battery pack. So it's not out of the question. An ARM7 core is, last I checked, on the order of maybe $5. It's not a very expensive part, and it's certainly worth the investment of the $5 versus maybe you'd pay $3 or $4 for a less capable part. So the additional investment of a few dollars is worth saving some cells because you've got really good SOC and other state estimates as well. So let's go on. Let's start looking at some real-world issues that we can address and make for a more robust solution.